We now move on to binomial distribution, and this is one of two special discrete distributions. Now, in the past, we've seen that distributions have more than one outcome. They can have 5 outcomes, 6 outcomes in a dice, 2 outcomes in a coin, maybe 4 outcomes in a spinner. But if you sort of simplify it as much as you can give everything just 2 outcomes. Something that you want, which is a success, and the things that you don't want, which is a failure. For example, if you have a die and you want to roll 1, 2, or 3, then your success will be getting 1, 2, and 3, and your failure would be getting 4, 5, and 6. So we basically just have 2 outcomes if we truly simplify it. Some examples are also here, where a business investment can either make a profit, which is a success, or a loss, which is a failure. A defendant in court case is found innocent, which is a success, or guilty, which is a failure. And in cricket, a batter is either out or not out. Right? So again, success and failure. So as I said, there are many possibilities between the success and failure. But if you take just a yes and no view, meaning like something that you want versus something that you don't want, it allows us to describe these situations using these distributions. These situations are again about discrete random variables, and they happen with repeated trials, meaning the action is happening over and over and over again. For example, if there is a die, then it's being rolled multiple times, and each time it's independent. Not only that, also the probability of your success that you decide in each of those trials is the exact same. Then we can use either the binomial distribution or the other special discrete distribution, which is the geometric distribution. They are very similar in a sense, but they have one main difference. Where a binomial distribution is used to find how many successes are in a certain number of trials, and it finds the probability of that. While in a geometric distribution, it talks about how many trials do we need to get to the first success that we decide. This is an example of a binomial distribution where a fair die is rolled 4 times, so there is a fixed number of trials, which is 4. And what is the probability of getting exactly 1 6? So your success is getting a 6, and you want 1 6 out of that. So that's the number of successes that you want. On the other hand, in geometric distribution, it would be written like this. A fair die is rolled. There is no fixed number of trials. It can be infinite. Then you're asking, what's the probability of getting your 6 on the third roll? So you want your first one to be a failure, your second one to be a failure, your third one to be a success, which is getting a 6. That is what geometric distribution is. Let's consider an experiment in which we roll 4 ordinary fair die, and in each independent trial, we can obtain 0, 1, 2, 3, or 4 6s. Therefore, getting a 6 is your success. That's what they're saying. And we have to let the variable r to be the number of 6s that are rolled. So again, we can either have 0, 1, 2, 3, or 4 6s from our 4 rolls. Now, since we're using 6 to represent success, and let's just say we are using x to represent a failure, and x is just anything on the die that is not 6, so 0, 1, 2, 3, 4, and 5. Therefore, we will have the probability of success, which is probability of getting a 6, to be 1 over 6, and the probability of failure, which is the probability of x, to be 5 over 6. Now let's go and fill out the probability distribution table here for the random variable r. We chose the number of 6s that we roll, the number of successes that we have. So if you want 0 successes out of the 4 trials, we want a none 6 in the first one, a none 6 in the second one, a none 6 in the third one, and a none 6 in the fourth one. And the number of ways that you can have 0 successes is 1, because you just want all of them to be failures. Therefore, what you have is 4C0, which is just 1. Where then you get the probability that it's going to be 4C0, which is the number of ways that you can get 0 successes. Then you're just multiplying by the probabilities. So you have 0 successes and you have 4 failures. And what this gives us is 625 over 1296. Then when we want one success out of the 4 trials, we can have it in 4 different ways, which is 6 in the first one, 6 in the second one, 6 in the third one, and 6 in the fourth one. Because you want 1, 6, you have 4 spaces to choose, just ends up becoming 4C1, which is just 4. Then to find the probability, we have 4C1 multiplied by 1 over 6, which is the success, power 1, because you have 1 success, times 5 over 6, which is the failures probability, because you have 3 failures, power 3. This will give you 500 over 1296. Then when you want 2 successes, which means rolling 2 6s, these are the possibilities that come out. There are 6 number of ways that you can have 2 successes, which is given by your 4 places that you have. Your first roll, your second roll, your third roll, and your fourth roll. And you want to choose 2 of them being 6s. So you have 4 combination 2, which gives you 6 number of ways, as we got here. Then the probability of getting this is just the probability of one of those options, which is 2 successes, so 1 over 6 power 2, and 2 failures, so 5 over 6 power 2 as well. Then you multiply by 4 combination 2, because there are 6 ways of doing it. This will give you the total probability. This will give us 150 over 1296. Then we go on to getting 3 successes. Therefore, we want 1 failure. This will be similar to this one. Just that we have x, 6, 6, and 6. We have 6, x, 6, and 6. So the failure in the second one. We have the failure in the third one. And we have the failure in the fourth one. We're choosing 3 6s out of 4 possible spaces. So 4 combination 3, which gives us 4. And the probability of one of them is just 1 over 6 power 3 times 5 over 6 power 1 times my 4C3. This gives us 20 over 1296. Finally, we want all 4 being rolled as 6. There's only one way of doing that, which is 6, 6, 6, and 6. And this comes from choosing 4 6s out of a possible 4 spaces, which is just one way of doing it. And the probability of this is just going to be 1 over 6, which is a success power 4, because you want 4 successes. And you want 0 failures out of this. And because it's just one way of doing it, we'll multiply this by 4C4. This gives us 1 over 1296. From this table, if you take a look at it carefully, we see that the probability of getting your number of successes as a certain value r, which we had 5 possibilities, 0, 1, 2, 3, and 4. That was just equal to 4CR multiplied by 1 over 6 power r, which is the successes, multiplied by 5 over 6 power 4 minus r. And these probabilities are exactly the terms that are in the binomial expansion of 1 over 6 plus 5 over 6 power 4. If you remember the topic from Pure 1. And using this other notation for your combinations, this just ends up becoming the probability of your random variable equaling to either 0, 1, 2, 3, or 4, which are values denoted by small letter r. Now we explain further where you use binomial distribution, or what criteria have to be met by a discrete random variable for it to be considered a binomial distribution. Firstly, they are a fixed number of independent trials, then that fixed number has to be finite. You can't go to infinity, like you can't have infinity number of trials, right? You have to do a finite number of trials. Then there are just two possible outcomes, which is the success and the failure. As we said, we can generalize everything into either a success or a failure. And finally, the probability of your success in each of those n trials is constant. In this case, is denoted by P. So P for the probability of your success in each trial, and N for the number of trials that are there in total. Then if that's the case, then your random variable X that has a binomial distribution as per this criteria will be denoted by X squiggly line, B standing for binomial, and the two parameters which are very important, which is the number of trials that are there and the probability of success. Then if that's your distribution, if X goes through a binomial distribution, then the probability of getting R successes, where R is a number between 0 and N, is N combination R, then your success power R and your failure power N minus R. It's an example that we see. If the variable X is distributed binomially with 3 independent trials and the probability of success being P, then X can either be 0, 1, 2, or 3, because they can be either 0 successes in those 3 trials, 1 success in those 3 trials, 2 successes, or all 3 successes in those 3 trials. Then we will have the following probabilities, where the probability of having 0 successes out of those 3 trials will be given in this format, where you have 3 combination 0 multiplied by your probability of success power 0, because it's happening 0 times, times the probability of your failure power 3, because you have 3 failures. Here, Q is just equal to 1 minus P, which is the probability of failure. And this can be repeated for your discrete random variable being 1, discrete random variable being 2, and discrete random variable being 3. Let's look at an example now. A regular pentagonal spinner is shown. Find the probability that 10 spins produce exactly 3 A's. So here we've been told that the number of fixed trials is 10, because you're spinning it 10 times, so n is equal to 10. The other parameter that we need is our P, which is the probability of success. And in this case, since it's a regular pentagon and it's divided into 5 equal parts, getting each of these letters after spinning has a probability of 1 over 5. Here we want to produce A's. That will be our success. And we have 2 A's out of these 5 options. Therefore, the probability of success will be 2 over 5. And as a result, the probability of failure will be the rest, which is 3 over 5. Then we want exactly 3 A's. So we want our R to be 3, or success to be 3. This with our formula that we've just been given, which is n combination R, our probability of success power R, multiplied by a probability of failure power n minus R, where R is the number of successes that we have. You can just fill in these values with what we've just gotten. We get 10 combination 3 multiplied by 2 over 5 power 3 multiplied by 3 over 5 power 10 minus 3, which is 7. And this just gives us 0.215 as our probability of getting exactly 3 A's from 10 independent trials of spinning that spinner. Next example, we've been given that the discrete random variable X is binomially distributed with n equals 8 and with the probability of success being 0.7, and as a result the probability of failure being 0.3. Then we want to find the probability that our discrete random variable is more than 6. Therefore we want our successes to be more than 6. Because our successes can be anywhere from 0 up to the number of trials that we have. We can't have more successes than we have trials. You can't score 8 goals from penalties if you take 7 penalties. Therefore, you can only have up to 8 successes out of your 8 trials. And because you want your successes to be more than 6, we can either have 7 successes or we can have 8 successes. Remember what I said, 7 or 8 successes, right? So we want our P of x is equal to 7 plus, because we have or, probability of x is equal to 8. This is just going to be 8c7, 0.7 power 7, and 0.3 power 1. Then we add it with 8c8, 8 combination 8 of 0.7 power 8 times 0.3 power 1. This here will give us 0.1976532 added with 0.0576481. Adding these two together, we will get 0.255 to 3 significant figures, which is the probability of getting 7 successes or 8 successes, which is also the probability of getting more than 6 successes. Next, in a particular country, 85% of the population has R positive blood. Find the probability that fewer than 39 people in a random sample of 40 have R positive blood. So here, the total number of people we have is 40, which means our n is equal to 40. We want to find the probability that x, which is the number of people that have R positive blood, is less than 39. This is the same as 1 minus the probability of x is equal to 39 plus the probability of x is equal to 40, where you're subtracting it by the entirety of this, because you're excluding these two options because you want it to be less than 39. Then the probability of success, which is if you have R positive blood, is 0.85, and the probability of failure is 0.15. So what you want here is 1 minus 40c39 times 0.85 power 39 times 0.15 power 1 added with 40 combination 40, 0.85 power 40 times 0.15 power 0. This gives us 1 minus 0.01060 and so on plus 0.001502 and so on. This ends up giving us 0.988 to 3 significant figures, which is the probability that fewer than 39 people have R positive blood. Then we are given that x is binomially distributed with n number of trials and probability of success being 0.4. Then we are told that the probability of you getting 0 successes is less than 0.1. We are told to find the lowest possible value of the number of trials that are there. Therefore, we want to find n where the number of successes is 0. Therefore, 0.4, which is the probability of success, happens 0 times, and 0.6, which is the probability of failure, happens n times. And we want all of this to be less than 0.1, because this right there is the probability of your discrete random variable, which is binomially distributed, is equal to 0. Anything combination 0 is just 1, and 0.4 power 0 is just 1 as well. Which means what we're doing is finding 0.6 power n to be less than 0.1. And we want the lowest value of n that we can get to have our 0.6 power n to be less than 0.1. For this, what we can do is apply ln on both sides, and we end up with ln of 0.6 power n is less than ln of 0.1. Then as per the log laws, we can bring n down, so we get n ln 0.6 is less than ln of 0.1. Then we can divide by ln of 0.6 on both sides. But we know that ln of 0.6 is a negative value. So because you are dividing by a negative value, your sign changes. Therefore, you end up with n is greater than ln of 0.1 over ln of 0.6. Therefore, n is greater than 4.5075 and so on, which gives us that the least possible value of n that you can get, which remember n has to be a whole number, because you can only have a distinct number of trials. Your least possible value of n will be 5. And remember, the reason we used ln here was because we wanted to find the value of n, and n is an exponent. And the only way you can make an exponent the subject is if you apply your logarithms. We now move on to the expectation and the variance of the binomial distribution. And we can calculate both of these from just the parameters n and p, which was the number of independent trials and the probability of success in one of those trials. Suppose we have an example, a very small distribution with just 2 independent trials and the probability of success being 0.6. Then the probability of you getting 0 successes is 0.16. Probability of you getting 1 success is 0.48, and the probability of you getting 2 successes is 0.36. You can confirm these 3 values using our known formula that we have. Then for the sum of the random variables times its probability, we can first find the random variable times its probability, and for 0, it's going to be 0 times 0.16, which is 0. For 1, it's going to be 1 times 0.48, which is 0.48. For 2, it's going to be 2 times 0.36, which is 0.72. And adding all of them up, you'll get 1.2. Remember, for the variance, we need the sum of the squares times your probability. So 0 squared times 0.16, which is 0. 1 squared times 0.48, which is 0.48. And 2 squared, which is 4, times 0.36 is going to be 1.44. And adding all of these up will give us 1.92. Then we can apply the formulas which we learned in the previous section of expected value of x and the variance of x, where x is a discrete random variable, and we will get the following results, where the expected value of x is just the sum of your discrete random variable x multiplied by its probability, which is just my 1.2. That's going to be my expected value of x, or my mean. Then for my variance of x, we get it through the sum of the squares times the probability, or we can say the expectation of the squares subtracted by the square of the expectation. So we have 1.92 minus 1.2 squared. And that is going to give you 0.48. Therefore, our experiment, which consists of 2 trials and a probability of success of 0.6, we get that the expectation or the expected value of a random variable x is 1.2, which we get by doing the number of trials, which is 2, multiplied by the probability of success, which is p. 2 times 0.6 is just going to be 1.2. On the other hand, the variance as well, you can find with the formula directly with your independent trials and your probability of success. And this time we just multiply the following: our independent trials, which is n, multiplied by the probability of success, which is p, multiplied the probability of failure, which is 1 minus p. And that will give us 2 times 0.6 times 0.4, which ends up giving us our 0.48. So we don't have to go through this entire process, but we just went through it to show you that NP also gives us the expectation that we learned to do in the previous section, and NPQ gives us the variance that we learned to do in the previous section. Therefore, the mean and variance of the discrete random variable x, which is binomially distributed with n number of independent trials, and the probability of success of p, is given by the mean or the expected value being the number of trials n multiplied by the probability of success p, and the variance is given by the number of trials n multiplied by the probability of success p multiplied by the probability of failure, which is 1 minus p, or we also denote it as q at times. Let's look at an example now where the random variable x is binomially distributed with 12 number of independent trials and the probability of success being 0.3, and we're supposed to find the mean, and the mean, which is the expected value of my random variable, is just equal to np, which is just 12 times 0.3. This only happens with binomially distributed data, and this is just going to be 3.6. That's going to be the expected value of my discrete random variable x. Then when we want our variance, that in a binomially distributed random variable is just npq, where n is a number of trials, which is 12, p is the probability of success, which is 0.3, and q is the probability of failure, which is 0.7. This ends up giving us 2.52. That will be the variance of my discrete random variable x. Finally, standard deviation. We always have that the standard deviation is just equal to the square root of the variance, which in this case is the square root of 2.52, which is just 1.58745 and so on. And in three significant figures, this just gives us 1.59. That's going to be our standard deviation. That's going to be our variance. And that's going to be our expected value for our discrete random variable x. Next, we've been given that the discrete random variable x is binomially distributed with n number of trials and the probability of success being p. Then we're given the expected value of our discrete random variable x, and we're given the variance of our discrete random variable x. Then we're told to find the value of our number of trials n and the probability of success p. So we know that e of x in a binomially distributed discrete random variable is equal to np, which is equal to 12. And we also know that our variance of discrete random variable x is equal to npq whenever it's binomially distributed, which is equal to n times p times 1 minus p, which is equal to 7.5. We have two equations with two variables, and the way you'll solve for each variable is using simultaneous equations, where here we get that n is equal to 12 over p. We're going to take that into our second equation, which then gives us 12 over p times 1 minus p. We can cancel out the p's here, and that just gives us 12 times 1 minus p is equal to our 7.5, which we have, which gives us that 12 minus 12p is equal to 7.5. This, rewriting it, will give us 12 minus 7.5 is equal to 12p, which gives us 4.5 is equal to 12p divided by 12 on both sides. We get that our probability of success p is equal to 0.375. Then, since we have that np is equal to 12 and p is 0.375, our n will be founded by this formula, 0.375, which I've substituted into the value of p, multiplied by n is equal to 12. I can divide by 0.375 on both sides, and that will give me my n to be 32. Therefore, my number of trials is 32, and my probability of success is 0.375 for my discrete random variable x. Then for part B, we just have to find the probability of my discrete random variable being 11. So 11 successes, which is just given by 32 combination 11 times the probability of success, 0.375 power 11, times the probability of failure, which is 0.625 power 32 minus 11, which is 21. And this is going to equal to 0.138 to three significant figures. That's going to be the probability of you getting 11 successes if we have this situation here.